Well, good morning. I think our class size is dwindling a little bit. Where's everyone going? Maybe they're going to hear Professor pitch. Well, anyway, we finished our dense theory yesterday morning, and then we ended up talking about tunable diode lasers. We mostly work in the infrared, where we mostly make use of tables of spectral information. And then I showed you some applications in aero propulsion. So in the first hour today, I want to talk about energy conversion of different systems. We'll talk about IC engines, gasifiers, and coal-fired power plants. Mostly to show you the utility of the things we've been talking about. Maybe that'll inspire you to think that it's worth the effort learning how to do spectroscopy for systems. This is a picture of one of the bigger projects we worked on in Wilsonville, Alabama. Coal gasifier is a prototype coal gasifier. It's not yet full scale, but it's large scale. And it's an example of where we went to make some measurements. I don't know how high up we were, somewhere up here. But the complexity is that in order to do coal gasification, it works at high pressure. So everything gets harder when you work at high pressure and high temperatures. So the real challenge was, could we make practical measurements in a large-scale facility, awkward situation, difficult working environment, with high-pressure gases and heavy particle loading. So in other words, not much of the light is transmitted through some duct, and we're still going to be successful. That was really the challenge that we faced. First challenge being, can we make measurements at, say, 15 or 20 atmospheres? What happens at 15 or 20 atmospheres is that the lines become spectrally broad. And so problems with interferences from other species or other transitions come into play. So we have to have a code that allows us to calculate the absorption coefficients as a function of pressure, which means we had to measure the pressure broadening coefficients, and we had to be very aware of interferences. You'll see that. I'm going to start with IC engines, just because that's something that we're pretty successful at. So what I'm really trying to preach is that tunable diode laser absorption spectroscopy is practical, even in harsh environments. Practical because not only can we use it in the laboratory, we can take these things in suitcases and take them on the road, make use of commercially available, relatively economical, robust light sources together with fiber optics and make measurements in difficult environments remote from our laser systems. I've shown you, I think yesterday, that there are ways to measure species by looking at the integrated absorption, for example, in a given line. We typically need to know temperature as well, and we get that by line ratios. Pressure we can get from line widths, velocity from the Doppler shift, and taken together we can get mass flow rates and momentum flux also. Over time, in my group, we worked at very high temperatures, probably up to 10,000 degrees actually, at least 50 atmospheres, maybe 100, high speeds, low speeds, multi-phase flows. And these are situations where there may be very strong emission, scattering of light, vibration, electrical interference, difficult environments. So it's not for a large-scale laser system that's limited to the laboratory. We've been in aero engine inlets, scramjets, detonation engines, IC engines, arc jets, gas turbines, shock tunnels, et cetera. So we've always been successful. Recently, we've been working on a rocket exhaust, really nasty environment, strong vibrations and emission, but with reasonable success. And my hope is that not only is this a research tool, but it also has potential to control energy systems and make them more efficient, less polluting. This is a picture of the power plant where one of my students worked. This was about 2011. They were 500 megawatt systems and burning coal. And those systems are highly regulated. So the question was whether we could make measurements that would help these operators run their plants more efficiently, or at least show the potential to do that. Gasification is more of a challenge because gasification is carried out at high pressures. So we have friends at the University of Utah that have small scale gasifiers. These are 3 separate gasifiers here. Big enough that we could work, it's realistic and yet small enough that it's easy to adjust the design as we are doing our research. And then also IC engines. This is a project for Nissan, and then this is actually a production engine. So we showed that we can make measurements in a production engine. Let's start with IC engines. My thought had been that we would be able to take a family of diode lasers of different colors, propagate the light by optical fiber, and probe either the inlet or the exhaust chambers. But naturally, of course, the engine company wanted us to work inside the chamber, which is harder because of the time-varying pressure and temperature and so on. That's what they wanted. They wanted us to help them measure temperature, which we did through water vapor lines, and then they became interested in measuring fuel loading, air-fuel ratio. So we started this work along about 2005. I didn't have an IC engine, so we made use of one over at UC Berkeley across the bay from Stanford, Professor Bob Dibble's laboratory. Then we went to Sandia's combustion research facility, which is about 50 miles away from Stanford, due east. Combustion research facility, they have an optically accessible engine. In many ways, you think that makes life easier, but it turned out that there were challenges because of the oscillating high pressures inside that chamber caused the transmission of light through this transparent cylinder to vary due to something called birefringence. Not always easier just because it's transparent. And finally, we ended up in Detroit working on the Nissan production engine in 2007. Now, in order to make measurements, we have to say something about the spectroscopy. And in the case of measuring fuel, what do we have to work with? So we don't have line positions anymore. We have line features. So this is a plot of the absorption cross-section versus frequency. So 3,000 wave numbers is 3.3 microns. So these are infrared transitions. And this is the spectrum that you would measure with, say, an Fourier transform infrared spectrometer if you had a sample of regular grade gasoline vaporized and held it about 50 degrees C. So we generate some gasoline vapor in a chamber, the FTIR chamber, measure the absorption spectrum. We call this the absorption spectrum. So you no longer see lines, you see features. When we see these features, we use the cross-section version of spectroscopy. But we need to know what it is. We understand why it looks like this. But the problem with gasoline, of course, is that different samples of gasoline have different composition and therefore slightly different spectra. And there's also a temperature dependence we have to worry about. So we had to learn how to do spectroscopy on large hydrocarbons. We knew that this was the place to look right here, this region, because it's the place of strongest absorption for hydrocarbons. First thing you do is you have to worry about what's the temperature dependence of the spectrum. So this happened to be some sample of premium grade gasoline that we bought at the local gasoline station. We changed the temperature from, you change the height of this particular prominent peak in the spectrum. Generally, the integrated area under this curve is more or less a constant, but the spectrum, the cross-section changes strongly at this one place. So if you want to measure temperature, it's clear that one place to park the laser is here, and then we might pick over here where it's temperature independent. The argument being that the ratio of the signals then is going to give us a temperature number, and we take advantage of that. The absorption cross-section varies with temperature, and we typically measure that not with a laser, but with the FTIR. This is called the CH stretch region, so every time you have a hydrogen atom oscillating with a carbon, you have this characteristic structure. So we use this to pick the frequencies to get temperature dependence, and then we pick one with large temperature dependence and one with small typically. So we're going to use at least 2 wavelengths. Determine temperature from the ratio of the absorption as those 2 colors. Now, problem is that gasoline varies from place to place. So for example, here's the plot of a fuel that has 6.3% of aromatic content, and here's one that had 39% aromatic content. So how are we going to make a quantitative measurement of gasoline if the cross-section is varying with the sample of gasoline? Without having to measure the spectrum for every new sample of gasoline. And we're doing this for Nissan. They told us that when the gasoline is delivered at their research center, they were told the relative fractions of the fuel in about 4 categories that I'm going to show you in a minute. So the idea was, well, if they tell us those 4 things, can we tell them this absorption spectrum? So we did a work for about a year trying to build a spectroscopic model, a cross-section model. The idea was that according to the testing procedures used by Nissan and others, when the gasoline is delivered, they will be told the fraction of that fuel which was paraffins, either normal or branched. In fact, they're told both of those numbers. The amount of the alkenes or olefins, the amount of the aromatics, and if it's a U.S. gasoline, the amount of the oxygenate, which would be ethanol. It's ethanol in the U.S. In other words, the researchers doing the engine work that was funding us would know for every sample of fuel that they were burning in their engines these numbers. There's 2 numbers here for normal and ISO. So the question was, if we were told those numbers, we predict the absorption spectrum. Recognizing that when you say olefins, yes, but there are many different olefins in that gasoline sample. We spent about a year trying to find a representative cross-section for each of these hydrocarbon classes as a function of wavelength and temperature. That was my student Adam. Then with that knowledge, namely the sigma sub j for any batch of fuel, that would apply to any batch of fuel, we could get the model value. So the idea was to come up with a model, cross-sectional model, which would tell us the absorption spectrum, function of wavelength, if we were told the mole fractions of these 5 components. So a lot of spectroscopy went into that and was published. And then we tested that model with 21 samples that were given to us by a company called Chevron. So we were told the content of the alkanes, that's the paraffins, the aromatics, the olefins, the ethanol. And we were told within the alkanes the part that was normal and branched. So we got 21 different samples, and we tested the model that we had built. We hoped that 21 samples would be kind of cover the full spectrum that might be encountered by engine companies. And then from these spectra, I should also have said, not only can we calculate the spectrum, we can pick the colors that we want to use for quantitative measurement. So we're going to pick 2 colors. From that model and from the 2 wavelengths that we picked. So we picked 2 wavelengths, which taken together would give us temperature and allow us to say the amount of the gasoline. So what does the engine company want? They wanted us to tell them the fuel-air ratio near the spark plug throughout the cycle. So we have to measure the concentration of the fuel to get there. So there's the optical design that we had to fight, and there's also the need to have a spectroscopic database. So this is just showing that the model cross-section and the measured cross-section of 21 different samples falls right on our curve. So we're pretty comfortable about this. This was at 450 centigrade. So we spent a year, maybe more than a year, building a spectroscopic model so that we could predict the spectrum and pick the wavelengths for any arbitrary fuel for which we had the content, the information of the 5 components. Now, we had to generate light. And when we did this, it was not yet possible to buy lasers at the colors that we wanted. So we had to produce them. And this is done by what's called difference frequency generation. So we had to play a trick. So if you have what's so-called pump lasers combined with a signal laser passed through a crystal called piplin, you can produce the color that you want. So we could produce the target wavelengths by having basically three lasers, 2 of which were tunable. And we would also end up with a separate color that was not attenuated by the gas, but would be attenuated by droplets. Because in some of the applications, we have to live with the fact that there may be fuel droplets present. So actually, we ended up with 2 wavelengths to characterize the vapor, and the next another color to deal with the fact that we might have liquid films on our windows or we might have droplets in the system. This was a challenge to build this laser system. Now you could probably just buy these lasers. Money. So, but we used the third near-eye laser to deal with the fact that we might have some, we call it non-resonant scattering. So we used two emitter colors to give us simultaneously the temperature and the fuel, and then the third color to deal with the effects of fuel droplets. Now, that's the scientific underpinnings, but you actually have to build this thing. So the way this was done is the spark plug was modified. So adjacent to the gap on the spark plug was a small structure, which would be a little bit more bulky than the spark gap itself, spark tip itself, in which we had basically the light being propagated in, passing across a gap of 5 millimeters, reflecting back off of a low-quality mirror. So we were making a measurement with a 5 millimeter gap adjacent to the spark plug, because what they really wanted to know was, what is the fuel-air ratio on a cycle-by-cycle basis at the time of ignition? And is it varying? Because they were struggling to meet the cold gas starting conditions. So the engineering was then to find the fibers, modify the spark plug, build this system here that would hold up in an engine, and get that light back onto some detector system. There's a lot of, I'll call it optical engineering involved, as well as the spectroscopy. And this mirror doesn't have to be perfect, but you just have to be, as long as you're taking ratios. But we have to have significant absorption. All right, and the goal then, measure fuel versus time, crank angle close to ignition. I'm just going to skip to some results. These were single cycle results. And the red would be the in-cylinder pressure, which comes up, so it ignites at about here. Pressure keeps going up, down. Two different colors, the green and the blue, are the absorptions over here on this axis. So the absorption is 0. Then the absorption goes up when there's some fuel coming in. Then the concentration goes up further. I think they had staged fueling. And what they really want to know is what's the, at the time of ignition, what's the fuel-air ratio and how does it vary with cycle to cycle. Then after that combustion, it goes back down to 0. So the fact that it behaves well in the limits, that's a good sign. It might look a little bit noisy to you, but these were really high-quality data. And we could get this throughout the cycle, and therefore look at the cycle-by-cycle statistics of the fuel-air ratio. I'm just going to show you this. If this was a time when they were really worried about meeting the cold start, so you have a lot of unburned hydrocarbons when the engine's cold. So the question is, can they at least have a repetitive cycle-by-cycle basis to have a design that would limit this? So these were this is the gasoline mole fraction. Notice the scale here. It's like 0.02 plus or minus about 10% over the first 400 engine cycles. Most of this scatter is not the error in the measurement. It's the actual cycle-by-cycle variation. So when they saw this distribution, which is actually pretty narrow, they were really happy. They had, how else would you get this information? How would you get the cycle-by-cycle fuel-air ratio at the spark plug in cold start? So that was pretty impressive. Why were we so successful? It's because hydrocarbons absorb like crazy. 3-micron light is highly absorbed by hydrocarbons. It wasn't, the good news is the absorption signals were strong. The bad news is there's just a lot of engineering that had to go on to see if that optical path would sustain itself over a period of minutes and hours. And it did. So what would happen is that the mirror would get kind of contaminated and dirty, and reflectivity would go down, but it was still enough. So after some period of time, they would take it out and clean it up. But it didn't have to be a high reflector to work. I guess that reminds me. I don't think I'm going to show it. We have sensors now that we call them single-ended. We don't actually have windows on both sides or even a mirror. We just bounce some of the light off of the surface, scattered. We backscatter, and that's enough for us to make our measurements. So that avoids the need to have either a mirror or windows on two sides. that in detonation engines. So this was really, in fact, this was so successful, we didn't have to do any more research. That was the downside for me. And they were going to use this as they dealt with the optimization of their various design fueling engines. Okay, so that's IC engines in a nutshell. We never got a chance to do the sensing in the exhaust duct. I really wanted to do time-resolved measurements of emissions. We never got to that point. Those measurements would have been easier because the conditions there are milder, the path length is longer, and the conditions are milder than inside an engine. So let's look at another hard problem. Let's look at coal gasification. So the motivation for coal gasification is to produce some sort of syngas that can be burned more cleanly than the coal. And there's different designs of reactors that are used, but the builders of these things wanted to be able to monitor the performance as part of their research to optimize their systems. And there's some sort of a high temperature reactor, some sort of inflow of oxygen, steam, coal, some sort of feeding process. And this stuff reacts, and you want it, and when it comes out, they hope it's syngas, some blend of CO and hydrogen and some other things. And so we monitor inside these reactors and then in the pipelines, and then maybe after some cleanup. So we built systems to monitor different places. The idea is that the syngas would perhaps go to a gas turbine, some sort of fuel air control, because the energy content of these coals varies. So the idea was to monitor the reactor as well as certain points in the process path, leading eventually to an optimized turbine power system. So the main parameters that they cared about was gas temperature along the way, and the syngas energy, which really means the content of the syngas, different components. You'd like to have carbon monoxide, methane. I'd like to have hydrogen, but I don't have a good way to measure hydrogen. Anyway, we get gas temperature by measuring the ratio of absorption spectra of H₂O. In the case of these oxygen systems, we also were able to measure CO, methane, CO2. We could measure these, but again, you really would like to have hydrogen. I don't know how to do that. We had to do it by some sort of balance idea. Why can't we do hydrogen? Well, it's the homonuclear case, not infrared active. So that's the downside of absorption. Can't always do every molecule we want. And we made measurements at 4 different locations. Where's the hardest place? Here's one at Utah. This was kind of a down-fired system. They would try to have combustion up here at the top. They're basically burning coal. When you burn coal, you get slag. You get slag, it covers your windows. So there's a lot of optical engineering that goes on to allow us to bring light through this duct, which is at high temperatures, slag, particles. It's a pretty nasty environment. So you have to have some sort of window system. So you maybe put the window here and then blow a slow flow of nitrogen through to keep this area open. You have to get light all the way across onto the detector. Once you get down past the region where there's all this slag, it's not so bad. We're down here. It's a little cleaner just before it goes out. This is easier. Once it gets into the syngas output stream, there's some particles, but you're at least no longer at high temperatures. There's no more slag. So one of the difficulties of laser diagnostics in a real system is the engineering of the windows and keeping them sufficiently clean. And coal slag is probably about the worst thing you can have. Have it hot enough for the coal to burn, and that usually means that you've got hot walls, and the particles there are going to condense on the wall and then melt and produce slag. Reactor core up here, we're typically around 13 to 1700 Kelvin. Down here, we expect it to be around 600 to 1000. Out here, we're very modest temperatures. And the pressure range of interest was basically 50 to about 200 PSIG, which is less than we would actually have in the field, the real plant. So the hope was that we could make measurements here and here. They might use that to control the inflow, or the combustion zone up here. Downstream, but they mostly wanted temperature up here and here. But downstream, what they really wanted to know is what did they produce? What was the gas mixture that was produced by their system. And what they really wanted was to emphasize CO and hydrogen. But along the way, you're going to get water, CO2, and some methane. Now, the problem then really is pressure. So let's look at the absorption spectrum of a single line. Single line, this would be around 1.4 microns. So remember, I was telling you how over time the lasers have become more available at longer wavelengths where the absorptions are stronger. But even at this point in time, I don't know, roughly 8 years ago, we really didn't have lasers, good lasers at long wavelengths. So we're working at 1.4 microns. That's called the near infrared. So here's the spectrum. Here's this wavelength spread over 2 wave numbers for 1 atmosphere. So there's the primary feature we're interested in. Here's some small ones off to the side. But when you go to 15 atmospheres, 25% water at 1600 Kelvin and the path length of 15 centimeters, now this is the spectrum. So we no longer see 0 anywhere, and we see a very broad feature. And the question, if we're going to see this in our system, we have to be sure that we know where I0 is, the baseline. So the good news is the absorbance is 0.2. That means roughly 20% absorption. That's a good signal. But you have to deal with this structure. How do we convert? How do we make sure we measure I over I0? Because I0 can't be measured by tuning in the wings. And we have to know this absorption coefficient really well. We have to take into account the contributions of the nearby. We have to take into account all of these things together impact now at high pressures. So you always have to do, maybe we spend about as much time on spectroscopy as we do on fielding the instrument. Then we have an additional problem. What about the role of the particulates? So if there's particulate there, there's going to be scattering of light, and the transmitted intensity goes down. So how do we get to I over I0 if we can't tune into the wings? So if you could tune the laser into, like in this case here, if we tune the laser into rings, even though there is particulate interference, that interference is a constant, wavelength independent. And so we can resolve the gas spectrum even in the presence of particles if there is a baseline. Now, in this case, we can't do that. So that was a challenge for us. And that's really one of the things that forced us towards this 1F normalized W wavelength modulation spectroscopy, which basically is looking at the shape, of this feature and ignoring the role of the wavelength independent interference that we encountered. So we did some experiments in which we measured the laser transmission off the line. So basically, we find a wavelength that's not absorbed by gas, and we measure the transmission at 10% here as a function of the pressure that was in this reactor at Utah. And what do you find when you get up to 150 atmospheres, 150 psi, 10 atmospheres? The fractional transmission of light was below I don't know if this is percent. Yeah, it was. This was below 0.1%. So in other words, fractional transmission of light was less than 10 to the minus 3 due to the blockage of the particles. So the amount of light coming out is very small, but it's still enough. So we found a way to make this work. Even in the presence of high particle loading, if you get some light out, you can interrogate it and get what you're after, because the particle interference is more or less wavelength independent. So if you could process the light that's transmitted in a wavelength dependent manner, you can get back to the molecules you care about. Anyway, we learned quickly that the particle loading in this reactor went up high with pressure. So that we were really worried about this when we went to Alabama, because we were going to go to higher pressures. So this scattering loss, that we had to be sure we had enough laser power so that even when you had 0.1% of that incident light, that it was enough. We played around. Well, we always used maybe a 10 milliwatt laser source was enough. So we used the WMS strategy that I talked about earlier this week. Here's two of the students trying to install stuff. So, you know, even at the University of Utah, which is a relatively small scale thing, this is still kind of a beast to work with. And so they're here, and over about 200 feet away is the control room. So when this thing is, it takes a long time to heat this thing up. they might heat it up for most of a day to get all the ceramic hot to get the reactor ready to roll. And so once they started flowing combustible material, no people are out there. So the people are over here. You got to get all this stuff set up, the wires, the detectors, fibers, and then go back to the control room and stay there. And then so until they shut down the fuel, they can't be out there in this test bay. So these are the practical aspects. So you have the spectroscopy and the fundamental lab work that we do at Stanford. Then you got to go in the field and deal with these real systems. And this one is still comparatively small. What we found when we measured in the core, this is the hardest place. This was that location 1. Here's a measurement of temperature. It's around 1600 Kelvin or so. Looks like it's a bit noisy. So immediately you have to ask, are those real temperature fluctuations? Is that noise in our detector? You have lots of questions like this. 200 PSIG. Now, would you expect, this is a reactor in which they're pumping in coal. So it's not like a steady flow of gas. You would expect some intermittency associated with the non-constant fuel loading. So even though we had less than 0.02% of light transmitted, we were able to get temperatures. That was a big deal. That was the power of our WMS scheme. And so we finally concluded that most of these fluctuations were actually real. It didn't affect the operation of their system, but it was news to them. How did they ever measure temperature? All they could do was put a thermocouple somewhere embedded in the ceramic liner. That's the closest they could get to temperature. Can't stick anything inside that coal-fired reactor. So we sent light. That's the thing you could transmit. Even though we only had a small amount of light, it was enough. So then I'm just going to show you some sample results. One of the questions was, can they trust our results? The only place they could really check us would be if we go further downstream into the syngas part of the problem and compare it with their method, which was based upon gas chromatography. When you do gas chromatography, you have to extract a sample from the stream and you go process it. And a little bit later, could be minutes, could be hours, you get a number. They were able to take samples every minute or two, and that's the GC stuff. Whereas we're measuring real time. So we'd look at this and say, that's pretty good. They agree pretty well. That made them happy that they could begin to trust us. We knew what we were doing. Although we could measure transients that they would never be able to see. And of course, we could also measure reactive species that they wouldn't be able to sample, because if you sample the reactive species, they disappear by the time they get to the GC. So we eventually measured simultaneously the 4 primary components that we wanted, the only one missing being hydrogen. Here's the CO2, kind of the same thing with the GC. Overall good agreement. You know, if you get in here, you have to decide who's right. Well, we think we're right, and that there are real fluctuations in this kind of a system. That was a big success, that we could get agreement with the GC. They started trusting us then. This apparently was 4 minutes. So they would take the GC data, then, by the way, then they would dry it, so they didn't get water. They would take the GC data, dry it, take 4 minutes to get their sample in. So basically it's good agreement, but we could do it in real time. Methane was important too. So they did some experiments where they intentionally varied methane and added methane and so on. Yes, again, we got the same. So we really were after CO, methane, CO2, water, the missing element being hydrogen. Water. So they don't get water. They dry the GC people, extract the sample, remove the water before they put it into the GC. You can't put the water into the GC. That's another benefit. We can measure water that they'd like to know, but they don't do that. These significant fluctuations over timescales of minutes in these reactors. Now, the next step was we're starting to build our confidence. We got some money from the Department of Energy, and we went to an industrial scale. Industrial scale was not yet full scale. It was like a prototype system, not yet the scale it would have to be if it were a real permanent device. So it's really still a an advanced research scale, a gasifier, I call it. National Coal Carbon Capture Center, I think it's called. So the goal was to prove that we might be able to measure moisture and temperature of the syngas somewhere up here in the system. So there was some sort of an instrumentation shelter up there. By the way, some of these places are very unpleasant. It might be hot, it might be dirty, a lot of safety rules. Yeah, there's a little man-sized figure right there. It was, and the students, of course, you know, we're used to working on the ground. Now they're up here on the side of this big system, where the weather, you know, might be raining, it might be anything. The design of this plant's a little bit different. There are different strategies. So what they care about is how do you design the reactor to give what you want out. And this is different than the University of Utah. This is called a transport reactor, a gasifier. Theirs was called, the Utah one was called oxygen-blown gasifier. But eventually what happens is syngas comes out, it's cooled down, there's still a lot of particles around, so they get rid of the particles with a particulate control device. Then the gas kind of flows down this way, on its way to wherever the syngas is going to go. I can't remember, but I think in real scale, I think we were 90 feet away from here or here. So everything's so big, you can't really make measurements like right here. By the way, they don't particularly, the engineers there don't really want you there. They don't want any holes in their high pressure reactor. They're really paranoid about safety. You know, this system is at, say, 15, 20 atmospheres, and it's hot. And what happens if we blow a window and they have a hole in their system? They didn't like that. So all sorts of complicated optical design so that if one set of windows breaks, they could close the valve and so on. That took about a year, designing that. But basically then that signal comes back. We have the lasers over here in this instrumentation shelter. Lasers and people. Light over here, and so on, the detector back. Nominal gas composition at this 15 atmosphere condition, 600K, which we've had here, expected to be in this range. So we have some sense as to what it's going to be. There's always some impurities we have to think about, and is it going to cause a problem or not? What they really want to know were these numbers right here. We're 99 feet downstream of this device. I mean, everything's so big. This is the closest we could get to the Here we had about 0.01% transmission again due to this beam steering and scattering from the ash. Still present. So this is now what it's starting to look like. So here's this syngas pipe, which is, I can't remember the diameter, maybe 10, 12 inches. But there's layers of insulation and steel and in order to be strong enough. So they put some flanges on here for us. And then they have multiple safety valves so that they could shut us down if there's a window break or a leak. So we had to be way off to the side here. We have to bring this laser in here, go through this long duct just to get in there, then go out the other side. All of this mostly just because of safety considerations. I think now, if we were to go back again, they would trust us more and we could make this a lot simpler. Redundant shut-off valves to isolate the laser. We use redundant sapphire windows and a lot of stuff built in for safety. Well, safety meaning that they didn't want to have a leak that would cause them to shut down. And we had to mount all this stuff on this pipe, this big pipe here, this big beam across. Quite a structure. This is a picture of this from the top. Here's our optical system out here, hanging way out to the side. Here's this big horizontal pipe way up in the air. So you might say, well, why are you going to all this trouble? Well, they didn't really have a way to do this. How are they going to measure inside this thing, which might be varying in time? There really wasn't any other option. You could conceivably try to extract samples from a GC, but then, you know, it's minutes or longer before you know what you have, and they can't do water. So they really wanted water and temperature. Now, this system is so big, it takes a long time to start up. So it takes hours to get this thing heated and ready to roll. So here's a pressure profile. The time scale now is in hours. Here's the pressure profile when they finally ramp up to where they want to be, 200 psi. They heat it up using propane. You have some sort of, you have to ignite this thing, and they flow propane, and finally it gets hotter and hotter and hotter. finally, it gets to a place where they're going to start feeding coal. They start feeding coal here. So roughly where they want to be, and then they shut it down. Everything, long time scales. You look at this and you don't know if it's real or fluctuations. Most of these were real fluctuations. So if we blow up this little segment right here, you might say, what's going on? Is this air, noise, what is it? No, if you blow it up and you look at this, look at that. That's our water sensor. That's real. You realize, well, actually, the way they put the coal in, it's not a steady stream of small particles. It's bursts of coal. So in fact, and now the scale is only between 0.08 plus or minus 0.02. These were real. So we were able to see fluctuations in water from this pulsed coal feeding during this initial phase of the burning. They'd never seen that before. So the temperature in the water were pretty successful. It worked well enough that after the shutdown in 54 hours, it worked well enough that they asked us to leave it there, and we came home for a month, and it kept working on its own for a month. Here's the water mole fraction as a function of time during this 500-hour test. Here's some places where we closed our valves on us, and then they opened them back up. I don't know why they did that. Sort of reactor upset, not related to us, but they shut us down temporarily. The key for us was working at high pressures, high particulate loading, trying to measure water and temperature especially. And we found that the design of our windows was good. The windows didn't degrade. They were purged a little bit at the ends. Okay, now here's, they really wanted to know the water. The way they were getting the water is they would extract a sample somewhere, they'd condense it out and try to measure how much water was in that sample stream. So they get points every number of hours. And so we could match that and say, again, they were really happy that we were in agreement with their method. But of course, we have real time and they don't. So in principle, they were really interested in this. In principle, we could have a real-time water sensor and they could avoid having to do the GC system. So now the question was, do we really believe these fluctuations? And so if you look really close, we looked at the water mole fraction versus time. Now we're doing in, looks like these are an hour. Time scales are in minutes and hours. So look, here's some sort of a thermocouple temperature sensor somewhere. Sure enough, it scales right with our fluctuations in the water. So people really began to have confidence that we could measure. Yeah, these temperature changes are pretty small here, 5-6 degrees. We were able to resolve. So that was a very successful campaign, and we have not gone back, but I think it proved that you can do optical sensing in a large-scale power plant. They're very worried about, do you have to have a person there? No, we didn't have to have a person there, but they're very conservative, these people. They just, the cost of shutting this down is just so large. My student, Xiaoxing, now a professor at Tsinghua, and he was at this power plant. Now, this is a coal-burning power plant. So in a coal-burning power plant, you feed coal, pulverizer, it goes into this boiler. Around 2,000 degrees Kelvin, the hot gases come up, go out, they're processed, particulate clean up, and finally they go up the stack. Most of the monitoring that's done is up here. Exhaust stack monitoring is done up here, and that's where they have to see if they meet the regulations. So there's a lot of steps in a coal-burning system. NOx is one of the things that's regulated, and the way NOx is removed is by injecting something called urea. This is called selective non-catalytic reactor. So the use of urea to remove NO is well known. So there's two types. There's catalytic and non-catalytic. But if you inject the urea at around 1,300 Kelvin, it will react with the nitric oxide and remove much of it. And then the gas cools as it's being used for heating water into steam. Cools down to about 600 degrees Kelvin. This is called the economizer, and then finally it goes after some particle cleanup and up the stack. what they were doing now is they typically monitor up here, way up here, and that's how they show that they meet the regulations, and the regulations are based upon this. What's the potential? They really were interested in CO and NO, the idea being that if we could make measurements somewhere, they might be able to optimize this combustor in a way that would minimize the CO and the NO. So we were targeted at the CO and NO. We have to always be aware of the interference from water. So we wanted to measure CO. We were working at this point in time, we were using the first overtone at 2.4 microns. That was all the lasers that we had available. We couldn't get 4 micron lasers yet. And the red corresponds to the spectrum you would see in this wave number interval. This is at 2.5 microns or so. So the red, that's 100 ppm of CO, 100 ppm of CO. And this is absorbance over here, which is like 0.003, 0.3%. And the blue is all of the water that we expected, about 10% of water. All of this for 1 meter path length and 500 Kelvin. So you can see the problem. You have to know enough about the spectroscopy to say, I'm going to be here, or here, or here, or maybe here, in order to avoid the problems with water. You can already begin to see this is for 100 ppm versus 100,000 parts per million of water. So we're trying to measure a small amount of something in the presence of a large amount of something else. We found some candidate lines, and we do some work in the laboratory, kind of convince ourselves where we can be, test it. And the question is, are we going to be able to measure, say, 10 parts per million? That's the question. So we do this. This is for NO, excuse me. This is for CO, this is for NO. NO's harder because the NO levels they want us to measure are smaller, and the NO is not quite as strong an absorber. So now we have 100 parts per million of NO. We have CO2 and water that we have to worry about. Where are we going to go? Here's a good possibility is right here. Another possibility is right here. So we have to do in the laboratory. You can't get all of this from HYTRAN. You have to do in the laboratory some tests to see how well can you measure NO in the presence of CO2 and water at these conditions. Make sure that we really can do this. We found a couple of candidate NO lines. This is now not yet dealing with particulates, so we're going to have to use our 2F, 1F idea to get rid of the influence of particulates. So this system went in at around 600 degree Kelvin place as the gas was exiting what's called the economizer. And there were some window ports there that we had access to. Here's the design. So this power plant was already configured for testing optical systems. So here's one more or less the, so there's some sort of intrusive tube here, leaving us with a path length of about 3 meters. About 1.5, so it's about 6 meters from here to here. And we were sampling in the middle over about 3 meters of optical exhaust. So at this point, we were using 2.3 microns for CO, and we're using 5.2 microns. This was one of our very first quantum cascade lasers, QC. Dusty environment, up in the air, hot. In this case, however, there wasn't quite as much scattering as we had experienced elsewhere, 50 to 90% with light. We still had quite a bit. So let's see if I can see this. So this is, the gas is going up here, it's coming back down. And here's where the student was residing. Really hot. She said that they were working on a metal grate, and that would get so hot that it would try to melt the bottom of your shoes. Xiaoxing. Here's she's opened up the door. So we have a chamber that was air conditioned. And she's looking inside to check the optical system, and hard hat on, and very hot, apparently. I wasn't there. This is the benefit of being a professor. So she measured, this is 2010, the Economizer Exit, CO versus time, parts per million. So one of the things they'd like, and this is now when they operate with a low amount of excess air. If they have a lot of excess air, what happens is that drives down the CO, makes it to CO2. They could get down here to, well, we measured, 5 parts per million. I don't know whether it's real or not. So when we use a lot extra excess air, when they use excess air, they remove the CO. When they take the excess air away, we get high CO, up to about 200 parts per million. Then they set it so down here in the normal range, and they would get down here around, say, 35. So this is what they really want to know. How sensitive is the CO level to the amount of air? They don't want to put in any more air than they need to. They're just processing air. They're really excited about this, that we might be able to use these kind of numbers to optimize the amount of air that was both still safe combustion, but more efficient. So it basically just shows that we can observe. Transients for them are minutes, not milliseconds. So this really just proved if we blow this up that we could get down here in the less than 10 parts per million without any trouble. Well, without any trouble. It took a year or so to design this system and then get ready to go, and all the engineering you have to do, and they're 2,000 miles away and so on. So the idea being we could make measurements close to the combustor and far from the stack. So their measurements were this continuous emission monitoring is called at the top of the stack. So I don't know, what's the time scale between where we are, top of the stack? I don't know, probably a minute. I mean, the big delay between where we are and the top of the stack when the gas goes out. So you can put some monitors up in the top of the stack and then have it running real time, but then and it could be optical, but it's not a very convenient place to be working. Okay, this was a 300 megawatt unit. They had 4 of these, I guess, totaling a gigawatt of power. Now we go to NO. NO is, of course, regulated. These were the 2010 results at the Economizer Exit. So basically, the very same place. We measure C, we measure NO as well. This is NO in parts per million, and NCR off. So if you take off the non-catalytic system, you remove the urea system, you get about 135 or 40 ppm. Turn it on, and depending on how much urea you put in. So if you put in too much urea, you get ammonia going out the exhaust stack. If you put in too little urea, you don't remove enough NO. So this all has to do with how you optimize the SNCR system and how it controls the amount of NOx. So I think the lowest we got, here's the urea flow here on this axis here. Okay, so the in-situ sensor avoids the delay of mixing. You could imagine the potential control. By the way, multiple boilers might feed into the same stack. So if you want to control individual boilers, you might need something like this down near the ground. A little bit slow, I guess. I hope I've kind of convinced you that these systems are more or less portable, robust, could be used for controlling systems, control variables, emission efficiency, et cetera. Could be very useful for power plants where they're worried about pollutants especially. Now looking ahead, what else could we do? There's always a way to do it better, but what else could we do? Well, we could move into the ultraviolet, and we could move to longer wavelengths, the mid-infrared. So we've been working here 2 to 5 microns. You go further into the infrared, you have some benefits for getting hydrocarbons. If you move into the UV, you can measure radicals and maybe even do a better job of NO. So we're always trying to look for a better way to do this. Of course, as new fuels come along, gasification, there's other applications. Okay, so that's where we are. Let's say I'm pretty much on time. So that was aimed at trying to show you that maybe spectroscopy has got a future, and you don't have to be to take quantum mechanics to do this. In the end, you're usually limited by engineering problems. How do you make it, put it into a package that's rugged? Transition in the next hour to start talking about shock tubes. The title of this lecture is supposed to be quantitative diagnostics. Quantitative to me means absorption and fluorescence. There we can make these quantitative. Some of the laser techniques that people use are not really quantitative. In order to take advantage of that quantitative nature, we frequently use shock tubes both to produce control samples of gas with known pressure and temperatures to do our high temperature spectroscopy. But we then also use the lasers to study combustion chemistry in a quantitative way. So the next lecture is going to be on shock tubes and start talking about applications to kinetics. The third lecture will be more of that. That will be the end of absorption, and then tomorrow will be all about fluorescence as the other quantitative diagnostic. Okay, any questions? While I'm thinking about it. So I put a lot of work into these notes that you have, which is boiled down from my course. If any of you have any feedback, if you find any mistakes at the end, email me or let me know, because I'm always trying to make them better. And if there's something you think would be a valuable addition, let me know. I'm always trying to make it more useful. Okay, so let's see, I guess we'll resume at 10 o'clock.